Alright, let's go ahead and talk about 7.4 trig functions at any angle. So in 7.3, we introduced our trig functions, but really that was only whenever we were working on a right triangle. But what if I want to work with just angles in general? Remember that typically whenever we deal with our trig function, we're doing the trig function of some angle. For example, I would say sine of some angle. We're not just going to say sine, it's sine of some angle. So I should be able to extend this to any angle. So to start us off for today's lecture, or this lecture, I'm going to start off by introducing two special right triangles. I know I wanted to talk about any angle, but to really do that, we have to talk about these two special triangles. So for this first triangle that I have on the screen, I call this the 45, 45, 90 triangle. That is, if I look at the angles of this triangle, it's a 45-degree angle, another 45-degree angle, and then a 90-degree angle. So whenever I have this particular angle ratio, 45, 45, 90, then I know that the sides of my triangle follow this particular ratio, a 1, 1 to square root of 2 ratio. I said ratio, not necessarily the length, because yes, this could be length 1, square root of 2, but it can also be a multiple of that. For example, this could be 2, 2, 2 square roots of 2. That is, I can multiply this length by 2, and it's still a 45, 45, 90 triangle. But this is the most simplified form of it, or the most common way that we see it. So this is my first special right triangle. And we know that if I have a right triangle and all three sides of it labeled, then we can find the sine, cosine, tangent, all the 6 trig functions of that angle. So that's our first right triangle. The second one I want to talk about is what I call the 30, 60, 90 triangle. Just like the 45, 45, 90 triangle, the 30, 60, 90 triangle has angles of 30 degrees, 60 degrees, and 90 degrees. So the way that this is formatted is that the side that's opposite from 30 has length 1. The side that's opposite of 60 degrees has length square root of 3. And the side opposite from 90 has a length of 2. So these are my two special right triangles. And we're going to be referencing this very often. So if you're watching this lecture, I do recommend copy down these triangles or keep them somewhere, take a picture, because I'm going to be referring to these back over and over again. Alright, so using these two special right triangles, why are they useful for us? So actually, to show this, we're going to go and jump straight into our example. So in our example 1, evaluate the exact value of the following expressions. Sine of 30 for part A. So again, before we had a right triangle, and then I said sine of theta. We didn't know what theta was. Now we're saying, what if I do know what theta is? Can I figure out what's going on? So to help us with this, I'm going to go ahead and pull up those same two triangles I had earlier. I'm just going to go ahead and put them on the side here, just for reference. So for part A, it has sine of 30 degrees. So if I want to deal with 30 degrees, then I should probably be looking at the triangle that has 30 degrees on it. So I'm going to be looking at this bottom triangle, and I'm focusing on 30 degrees. So now that I have the triangle that I want to work with, how do I deal with a sine of 30 degrees? Well, we know that sine of 30 should be opposite over hypotenuse. So using my special right triangle, that's exactly what I'm going to do. My opposite is 1. My hypotenuse is 2. So I have 1/2 as my final answer. And this is already simplified all the way. I can't really break down 1/2 any simpler than that. Alright, so we have sine of 30. Now what about for part B, tangent of 45 degrees? Well, I'm working with 45 degrees, so you can probably guess that we're working with the triangle that has 45 degrees. And I'm going to focus on, in particular, this 45 degrees over here. Yes, you could have chosen this one, this 45 on the top. It doesn't really matter because this triangle, if you flipped it around, it's the same diagram. So tangent of 45 degrees. Well, we recall that tangent is opposite over adjacent. So if I look at 45 degrees here, focusing on this angle, what's opposite of this 45? That's 1. What's adjacent? It's also 1. So I have 1 divided by 1, or I can simplify this to be just a positive 1, giving me my final answer. And now let's look at cosecant of 60 degrees. So 60 degrees, I should probably be working with the triangle that has 60 degrees. So I'm going to move this down, and let's focus on the 60. So what is the ratio for cosecant? Well, we recall that cosecant is just the flipped version of sine. So if sine is opposite over hypotenuse, then cosecant should be hypotenuse over the opposite. So if I look at this triangle, what's my hypotenuse? My hypotenuse is 2. And then my opposite side is the square root of 3. And remember, we're not done here just yet. Not because of anything that we did anything wrong with hypotenuse over opposite, but because I don't want a square root on the bottom. So how do I get rid of the square root on the bottom? Well, we have to rationalize. That is, I'm going to multiply by square root of 3 over the square root of 3. And then now I just multiply straight across. 2 times the square root of 3, I get 2 square roots of 3. And on the bottom, square root of 3 times square root of 3, I get positive 3, giving me my final simplified answer. So now we're starting to work with dealing with the trig functions at these particular values, 30, 60, 45. This opens up and allows us to work a little bit more with a wider range of angles. So now that we're done with example 1, let's move on from here. Just for some extra practice, same instructions, evaluate the following trig functions at the given angle, or these following expressions. So for part A, I want cosine of pi over 4. So pi over 4, this is not in degrees. This is a radian measure, if you recall from section 7.2. So, what do I have to do from here? Well, remember from 7.2, we can always take a radian measure and convert it towards degrees. So if I have pi over 4 for part A, if I want to convert this to degrees, then I had to multiply by 180 over pi. So now if I clean this up, let's see, my pi's will cancel each other out because we have pi divided by pi. And what about 180 divided by 4? Well, 180 over 4, that will give me 45 degrees. So if I'm looking at cosine of pi over 4, this is the same thing as saying cosine of 45 degrees. Because pi over 4 and 45 degrees, these are the same angle. I'm not saying that pi over 4 and 45 degrees, those aren't the same numbers in your calculator, but in angle measure, they are. Alright, so now we've done a lot of the hard work already. Cosine of 45, I'm going to look at the triangle that has 45 degrees. So I'm going to focus on this top triangle. And focus on one of the 45s. It doesn't matter which one because you'll get the same result either way. Well, we remember that cosine is adjacent over hypotenuse. So adjacent to 45 is 1. And then the hypotenuse is the square root of 2. So adjacent over hypotenuse, we get 1 over the square root of 2. And we have that same problem as before. I don't want a square root on the bottom. So I'm going to multiply by the square root of 2 over the square root of 2. By doing so, I get 1 square root of 2 on top, or just square root of 2. And on the bottom, square root of 2 times square root of 2, I get 2, giving me cosine of pi over 4. Alright, so from here, let's look at part B now. See if you can work through part B. sine of pi over 3, using the same method that we did for part A. Well, to start us off, let's go ahead and convert this to degrees. If you know what pi over 3 already is from just being familiar with radians, that's great. But just for notes, let's convert it to degrees. To convert pi over 3 to degrees, we have to multiply again by 180 over pi. And if I do this multiplication, pi divided by pi cancels each other out. 180 divided by 3, I get 60 degrees. So sine of pi over 3 is the same thing as sine of 60 degrees. 60 degrees, I'm going to go ahead and focus on a triangle that has 60 degrees. So now I have to recall, what is sine's ratio? Well, we know that sine should be opposite over hypotenuse. So what's opposite to 60 degrees? Opposite to 60 degrees is square root of 3. And then the hypotenuse is 2, giving me the square root of 3 over 2. And then we don't have to rationalize here because, remember, I only care about not having a square root on the bottom. It's okay if we have a square root on the top. Alright, so this is how we deal with, again, my trig functions at these particular angles. Alright, so let's move on from here. What else can we deal with? The next thing that we're going to deal with is this thing that I'm going to call a quadrant. So here I have our standard Cartesian plane, the XY plane, where we usually graph stuff on it. And notice here I went ahead and put my degrees, 0 degrees, 90, 180, 270, 360, just so that we're familiar with it. So whenever I discuss a quadrant, whenever I draw my x-axis and y-axis, you can probably say that I have my axes split up my plane into 4 squares. I have this top right square, this top left square, bottom left square, and then this bottom right square. So this is actually what we call the quadrants of the plane. So this is going to be quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So the way that we label this is that we know that our angle, we always start at 0 degrees, and then for a positive angle, we tend to go in the counterclockwise direction. So that's how these are labeled. So now that I know what the 4 quadrants are, why did I bother mentioning them? So, as it turns out, a trig function can be also a negative value. So far, everything we've done up to this point, we've always been doing a positive trig value. In particular, because all the angles that we've really worked with, where I told you give me sine of whatever angle, in particular from examples 1 and 2, those have been in quadrant 1. All of those angles have been between 0 to 90 degrees. So, how do I know whether a trig value should be positive or negative? Again, before we had something like, I don't know, sine of whenever angle is equal to 2/3, and we didn't really bother about saying is it negative 2/3 or positive 2/3. So that actually depends on which quadrant is my angle within. So we're going to go ahead and talk about where each trig function is positive or negative. So if I'm working with an angle in quadrant 1, then all of my trig functions will be positive. In quadrant 2, only sine and cosecant are positive. Again, if my angle is in the second quadrant, in this case between 90 and 180, this top left area, then sine and cosecant are positive. And this makes a little bit of sense for us because remember, cosecant is just the same thing as sine, but just the reciprocal. That is flipped over. So I shouldn't be changing signs, the positive and negative between sine and cosecant. What about quadrant 3? In quadrant 3, only tangent of theta and cotangent of theta are positive. All the other trig functions are negative in this third quadrant. And in quadrant 4, only cosine of theta and secant of theta are positive. So we have to keep note on, first off, which quadrant does my angle lie within, and which trig functions are positive and negative in that quadrant. So for example, if I was working in quadrant 3, I was dealing with some angle here. Let's say something between 180 and 270, let's say 200 degrees. Then I know if I did sine of 200 degrees, I don't know what that is off the top of my head, but what I do know is that in quadrant 3, sine is going to be negative, because in quadrant 3, only tangent of theta and cotangent are positive. So one way that a lot of people try to remember this is that besides saying quadrant 1 is this, quadrant 2 is this, so on and so on, we have this phrase, all students take classes. So how does this potentially help us? Well, in quadrant 1, all trig functions are positive. In quadrant 2, student starts with s, so that sine and a cosecant are positive, because again, sine and cosecant, they're just flipped versions of each other. In quadrant 3, we have take, the t, tangent and cotangent are positive. Every other trig function should be negative here. And in my fourth quadrant, we have classes c, cosine, and its reciprocal, secant of theta, should be positive. So again, you're probably going to hear me say this random phrase, all students take classes, and that's going to be referring to which trig functions are positive within that quadrant. So a really nice skill for us to deal with. We will be talking a little bit later about what happens about these areas that are not in the quadrant, like what happens at 0 degrees, 90 degrees, 180, 270, 360, and so on. Those things that aren't in these squares, but they lie sort of on the border. But here we have our quadrants. So, in example 3, I have this information, and I want you to tell me which quadrant does my angle theta lie within. So for part A, I don't know what this angle is, but I know when I deal with cosine of the angle, it's bigger than 0, or in other words, it's positive. And where sine is less than 0, that is, sine of theta is negative. So let's start off by focusing on this first part. Where is cosine positive? And I have this our little picture here included. So cosine is positive only in 2 quadrants. Quadrant 1, yes, cosine is positive. Quadrant 2, cosine is not positive. Only sine and its reciprocal is. Quadrant 3, cosine is negative here. And quadrant 4, cosine is positive. So just from underlining this, looking at cosine being positive, I've eliminated the options of quadrant 2 and quadrant 3. So that's what I can pull from a single trig function. Now let's go ahead and look at the next part. We know that sine is negative. So from my remaining 2 quadrants, 1 and 4, where is sine negative? Well, in quadrant 1, everything is supposed to be positive, so I can't be in there. And just to double check our work, quadrant 4, is it true that sine should be negative in this 4th quadrant? Well, yeah, sine should be negative here, because the only trig functions that are positive in quadrant 4 are cosine and secant. So I know that my angle is in quadrant 4. Again, I don't know what my angle is, but I know it's somewhere in this bottom right corner. Alright, so now using that same intuition, let's deal with parts B and C. On part B, tangent of theta is positive, and cosine of theta is positive. So similar to before, I'm going to focus on this first trig function. Where is tangent positive? Let's see, quadrant 1, yeah, tangent is positive. Quadrant 2, this tells me tangent would be negative, so I can't be in this top left quadrant. And I clicked on this a little bit prematurely, but quadrant 3, tangent is positive, that's fine. And then quadrant 4, tangent is negative here, which we don't want. So from just looking at this first trig function, I can eliminate 2 quadrants. That's typically what's going to happen. Now what about my second portion? Where is cosine positive? Well, let's see. In quadrant 1, cosine, everything is positive. So cosine is positive. What about quadrant 3? Well, in quadrant 3, only tangent and its reciprocal cotangent are positive. So that tells me cosine is negative in this third quadrant, which is what I don't want. So I know I'm working in quadrant 1 for sure. Now let's look at part C. Same idea. Cosecant of theta is greater than 0 and cotangent of theta is less than 0. So oftentimes, this all students take classes. It works best whenever we're dealing with sine, cosine, or tangent. So to help us out here, just so that we can really solidify this, I'm going to go ahead and write an equivalent expression here. Well, if cosecant of theta is positive, then I also know that sine of theta is positive. Again, because sine and cosecant are just flipped versions of each other. They don't change this positive to negative between each other. Similarly, cotangent of theta. Cotangent of theta being negative means that tangent of theta is negative. So now using this new information, starting off with sine being positive. Where is sine positive? Well, sine is supposed to be positive in either quadrant 1, because everything's positive there, and quadrant 2, because S sine is positive in quadrant 2. That kills off my 2 bottom options. Now, what about tangent of theta being negative? Well, I can't be in quadrant 1, because in quadrant 1, everything is supposed to be positive. So that kills off quadrant 1. And just to double check, is tangent negative in this second quadrant? Yes, because only sine and cosecant are supposed to be positive in quadrant 2. So I know for part C, my angle is in quadrant 2. So this is how we're breaking down and deciding which quadrant we are working in. And so that gives us example 3. Let's move on from here. Example 4. Determine the value of cosine of theta if I know that sine of theta is equal to 3/4. And I also know that cotangent of theta is less than 0. That is, I know that cotangent of theta is negative. So at this point, we're going to be combining a good bit of the work that we've done in Module 1 and a little bit from what we learned today. What can we pull out from this? Well, first off, let's look at sine of theta being 3/4. Well, I know if sine of theta is equal to a number, I know that sine is opposite over hypotenuse. In other words, if I draw a right triangle and label theta to be one of my angles here, then the opposite side will be 3, and then my hypotenuse will be 4. So this is just using my right triangle definition for my trig functions. So I know that if I have this third side, then I can find all of my trig functions. In particular, I'm missing the adjacent side. So if I want the third side, we know that if I have 2 sides of a triangle, to get the third side, I can use the Pythagorean theorem, which is, if you recall, a squared plus b squared is equal to c squared. So I don't know what a is. I'm trying to figure that out. B is 3, so I have a squared plus 3 squared is equal to the hypotenuse squared, so 4 squared. And now I'm going to clean this up. 3 squared is 9. 4 squared, I get 16. If I want to solve for a, I should go ahead and subtract 9 from the left and from the right, giving me a squared is equal to 7. And then I can take the square root, giving me a is equal to the square root of 7. So I'm going to fill that into my triangle. Alright, so looking at this, I can now deal with cosine of theta. I know that cosine of theta, based off this right triangle, is, well, adjacent over hypotenuse. So what's adjacent to theta? Adjacent to theta is the square root of 7, the hypotenuse being 4. So I have the square root of 7 divided by 4. So I have cosine of theta, right? Well, we just gotta make sure about one last thing. I haven't used this piece of data yet. Cotangent of theta being negative. In other words, I don't know if this cosine is going to be positive or negative. So, how do I know if it's positive square root of 7 over 4 or a negative square root of 7 over 4? Well, to figure that out, I have to know which quadrant am I working in. Am I working in quadrant 1, 2, 3, or 4? So, using this piece of data here, again, we know that cotangent, this has the same sign as tangent of theta. That is, if cotangent is negative, then tangent is negative as well. And if I want to figure out what quadrant we're in, let's see, sine is positive. So I have to be in either quadrant 1 or 2, because those are the only quadrants where sine is positive. So I can eliminate the bottom two options. Where is tangent negative from the remaining quadrants? Well, in quadrant 1, everything is supposed to be positive, so I can't be in quadrant 1. And in quadrant 2, yeah, tangent is negative because, well, only sine and cosecant are supposed to be positive, sorry. So if I know I'm working quadrant 2, is cosine positive or negative in this second quadrant? Well, again, quadrant 2, we have the S in students. Only sine and cosecant are supposed to be positive. So that means cosine should be negative. That is, cosine of theta is negative square root of 7 over 4. Finishing up our example here. So the main difference here that we've done before is that in previous lectures we said if I gave you sine of theta is equal to 3/4, I told you we had a right triangle. In this case, we don't necessarily have a right triangle in the very literal sense. And I say that to avoid going too deep into the stuff we're going to be covering a little bit later. Alright, so that was example 4. Continuing our study on trig functions at any angle, I'm going to start by asking this question. What if I wanted sine of 210 degrees? We know how to deal with sine of 30, 60, 45. But obviously there's many more angles besides those three. So to help us expand the number of angles that we're allowed to work with, we introduce this idea called reference angles. So let's talk about 210 degrees. Here I have my xy plane labeled with 0, 90 degrees, 180, 270, 360. And let's say I want to draw 210 degrees. Well, 210, that's between 180 and 270. So I know I'm somewhere in this third quadrant. In particular, what I'm going to do here is, what is this angle from what I have here to 180 degrees? That is, what is this angle that I've drawn? Well, if I wanted to figure this out, then I could say from my start point all the way to here is 180. If I want to make it all the way to 210 degrees, then I should be going another 30 degrees. Or in other words, I can find that by saying 210 minus 180, so this whole angle minus this upper half, I'm left with 30 degrees. So what I found here is 30 degrees, and I'm going to call that the reference angle for 210. If I want to give it a formal definition, a reference angle is the smallest positive angle from the x-axis to my original angle theta. So if I look at this picture I have on the right, remember my x-axis is this horizontal line. So my reference angle is saying how far is my original angle from this x-axis. What's the closest way or quickest way I can get there? Well, my quickest way is drawing from my angle and going upwards, and that is a 30-degree angle. So this is actually going to help us a lot. As you notice, you might be noticing it a little bit ahead of time. Even though I don't have a triangle for 210 degrees, I do have a triangle for 30 degrees. So before we actually talk about getting sine of 210, let's just get some extra practice in getting reference angles before we actually work with that sine of 210. So, example 5. Give me the reference angles for these three angles that I've listed here. A and B are given in degrees, and C is given in radians. So let's start off with part A, 300 degrees. Again, just to help us visualize this, I'm going to draw 300 degrees on my chart. 300 is between 270 and 360, so I know it's somewhere in this bottom right quadrant, quadrant 4. So somewhere around here. If I want my reference angle, I want the smallest angle that would take me quickest to this x-axis. So either I want to get the closest to 0 or 360, or 180 degrees. Well, the quickest way for me to get to this horizontal line would be starting at this angle and continuing in the counterclockwise direction towards 0. That is this angle right here. You might have thought, why can't I go from this angle to 180? Well, that would be a bigger reference angle. And remember that my reference angle is supposed to be the smallest angle, or the quickest way to reach the x-axis. Alright, so what is this angle supposed to be? What is this orange angle? Well, what I've drawn so far here is 300 degrees. How much further do I need to go to get to 360? Well, I can find this by saying, let's take 360 minus my angle, 300. This is 60 degrees remaining here. So my reference angle for part A is 60 degrees. So I have my reference angle, and again, notice 60 degrees. That looks a little bit familiar from our 30, 60, 90 triangle. And I'm specifically choosing these, as you'll probably notice, these examples, so that they match one of our triangles. Alright, now let's look at part B, negative 240 degrees. Well, since this is a negative angle, it may be more beneficial that instead of these positive 90, positive 180, positive 270, that I put the negative versions on there. So, actually, I animated this in the opposite way. Let's do it this way. Negative 240. I know that an equivalent angle would be if I added 360 to it. That is, negative 240 plus 360 would give me 120. Because, remember this from, I believe, 7.1, if I take one angle and I spin it around 360 degrees, then I'm still facing the same direction. Our formal term for this was our least positive coterminal angle. So it may be easier for us to imagine 120 degrees. So 120, that's between 90 and 180. That is somewhere in this second quadrant. Now, if you were doing it the way that I mentioned earlier, you would say, all right, this is 0, negative 90, negative 180, negative 270. Negative 240 is between negative 180 and negative 270, so in the same quadrant, just the opposite direction. But regardless, it would lead us to the same direction. So, how do I find the reference angle for this given angle here? Well, I want the shortest distance to my horizontal axis here. Well, my quickest access would be going directly downwards towards 180. So what is this angle that I've drawn here? Well, this is 120. If I want to go all the way to 180, then one way I can find this is saying 180 minus 120, giving me 60 degrees. So 60 degrees is my reference angle. You could have also said, I'm at 120, how much further do I need to go to get to 180? Well, I need to go 60 more degrees. Alright, so we have our reference angle for negative 240. Now for part C, 7 pi over 4. Again, you may not be very comfortable with radian measure, so let's convert it to degrees. If I want to change this to degrees, then I can go ahead and multiply by 180 over pi, and then simplify this. My pi's cancel out. If I do 7 times 180 divided by 4, I believe we should be getting 315 degrees. Again, we can do this via our calculator, or if you want to do this by hand, you can say 180 divided by 4 gives us some value, times 7, we get 315. Alright, so what does 315 look like visualized? Well, 315 is between 270 and 360. So I'm expecting it to be somewhere in this bottom right quadrant, 315. And again, I don't necessarily have to draw this to scale. I'm just using this to help me visualize what my reference angle is. So if this is 315 degrees, what's my quickest way to my horizontal axis? Well, it looks like if I'm right here along this arrow, the quickest way would be going upwards towards this 0, 360 line. So if I've already gone 315, how much further do I need to go to get to 360? Well, you can either think, all right, 315 plus 45 will get me 360. Or if you want to do it the other way, you can say 360 minus 315 gives me 45 degrees. So my reference angle should be 45 degrees. Or, this is just in case the homework asks for it, if it asks for it in radians, you can convert this back to radians and say, if I multiply this by pi over 180, you would get pi over 4. Just a quick reference in case the homework happens to ask for it, because I know sometimes they're picky about their format. Alright, so we know how to work with reference angles. Now, let's finally get to example 6. This is what I talked about in the previous part 1 of this video, sine of 210 degrees. Remember that we found the reference angle for 210. This is what 210 was, and my reference angle is 30. Furthermore, I know that this angle is in quadrant 3. So the first thing I'm going to deal with is sine of 210 degrees positive or negative? Well, we know we have our phrase, all students take. So in quadrant 3, we have T for take, only tangent and cotangent are positive. So in other words, I know that sine of 210 is some negative number. And the nice thing about reference angles is that we can actually use our reference angle to evaluate sine of 210 degrees. So why is that true? So let's look at this 30-degree angle that I have here. Let's imagine that I went ahead and drew this line over and drew another line directly vertical to my 180 line. What did I just draw here? Well, I just drew a right triangle where this is 30 degrees. So if I just want to see this a little bit more clearly, I can go ahead and clear this up. And using this idea, I can say that sine of 210 is the same thing as negative sine of 30 degrees, because this 30 degrees was derived from the 210. So we know how to deal with sine of 30. I'm going to go ahead and flip this around so that it looks a little bit more familiar for us. We know what a 30, 60, 90 triangle looks like. A 30, 60, 90 triangle has a ratio of 1, 2, square root of 3. So now that I have a triangle for us to work with, I now have to ask what's sine of 30. Well, we know that sine is opposite over hypotenuse. So what's opposite to 30 degrees? We have 1. What's the hypotenuse? 2. So this is just reiterating what I just said. Sine is opposite over hypotenuse. Can't forget the negative that we said from the beginning. Opposite was 1. The hypotenuse was 2. So sine of 210 should be negative 1/2. So this is why we introduced the quadrants and the reference angles. The quadrant of the original angle tells me, is my answer positive or negative? The reference angle lets me use my 30, 60, 90 triangle or my 45, 45, 90 triangle, depending on which one is relevant. So this was example 6. So what we had here, just again, we use the quadrants to figure out our sine, and then we found the reference angle. Using that reference angle, we then have a much nicer problem in which we can apply the triangles. Let's move on to our next part. Example 7, and last example for this section, before, not for the module, but for this part 2. Let's evaluate tangent of negative pi over 3. Well, again, it may be easier for us to imagine this in terms of degrees. So let's convert negative pi over 3 to degrees. And recall that we do that by multiplying by 180 over pi. So if I clean this up, pi cancels with pi. 180 over 3, I get 60. And I can't forget my negative that's up in front. So I have negative 60 degrees. Alright, so this tells me that tangent of negative pi over 3 is the same thing as tangent of negative 60 degrees. So again, I haven't done anything about my reference angles. I haven't talked about my quadrants yet. All I've done was change the measure to be degrees so that we're a little bit more comfortable in imagining what this angle looks like. So tangent of negative 60 degrees. Where is negative 60 on this? What does it look like? Well, first off, it's negative. So I know that if I wanted to draw it, I should be going in this direction. And negative 60 is between 0 and negative 90. So I know I'm in this fourth quadrant. Alright, so in this fourth quadrant, is tangent positive or negative? Well, we have all students take classes. C for classes, only cosine and secant are supposed to be positive. So I know that tangent is going to be negative here. That's one note that we should include. And also, what's my reference angle? Well, the quickest way for me to take this angle and go to this horizontal axis, it looks like we can just go in the reverse direction back up. So my reference angle here should be from this point to 0, which happens to also be 60 degrees. Alright, so this tells me that tangent of negative 60 is equal to negative tangent of positive 60. Now we can use our special right triangle, which I included here on the bottom right. Well, we know that tangent is opposite over adjacent. So what's opposite of 60 degrees? Opposite of 60 degrees is square root of 3. Adjacent to 60 is 1. So I'm left with negative square root of 3, the opposite, divided by the adjacent 1. And the last thing I can do to clean this up is, well, anything divided by 1, that doesn't really affect anything. I have negative square root of 3. Finishing up our example 7. So the main point of this whole section was saying that a lot of the angles, even though they don't look like our 30, 60, 90 or 45, 45, 90 degree triangle, there's very many angles that we can actually, what's the word, illustrate using reference angles and sort of still apply our special right triangles. Of course, there's a lot of angles that we still can't deal with, but this does open up our options a bit more. But besides that, that's all for this part 2.